Solutions for perfect problem 3 for Math 211. In this problem, we're given a set, and the set contains the elements 2, 3, 5, 8, and 9, and we're defining a relation, and the relation is that two elements are related if the base 2 representation of the first element is longer than the base 3 representation of the second element. Okay, that's kind of a mouthful, but hopefully with this example you can figure out what I'm talking about. So the first task here is to show all elements of this relation. And it says you can either do it with ordered pairs or an arrow diagram. I much prefer an arrow diagram because it's easier, or at least shorter to write. So when you're drawing your arrow diagram, you write your set twice. So my set contains the elements 2, 3, 5, 8, and 9. And so I'll put that over here and over here. And then I want to draw an arrow from anything over here that's related to something over here. So how do you figure out what's related to what? Well, I think it helps to figure out the base 2 and base 3 representations of each of these numbers. So maybe I'll do that first. In base 2, the way you write the number 2 is 1, 0. If you're in our donut shop example, you buy 1 box of 2 donuts and 0 single donuts. If you're buying 3 donuts at a base 2 shop, you'd buy 1 box of 2 and 1 single. If you're buying 5 donuts, you'd buy 1 box of 4, 0 boxes of 2, and 1 single. If you're buying 8 donuts, you just buy 1 box of 8 and 0 boxes of 4 and 0 boxes of 2 and 0 singles. And finally, if you're buying 9, you'd buy the 1 box of 8, no boxes of 4, no boxes of 2, and 1 single. What about base 3? Well, if you're buying 2 donuts at a base 3 shop, you just buy 2 singles. If you're buying 3 donuts, you'd buy, this is kind of hard to read, you would buy 1 box of 3 and no singles. Buying 5 donuts, buy 1 box of 3 and 2 singles. Buying 8 donuts, sounds like 2 boxes of 3 and 2 singles. And finally, 9 donuts, you'd buy 1 box of 9, 0 boxes of 3, and 0 single donuts. So now that I have all these representations, I can start to figure out my arrow diagram. I want to draw an arrow from an element here to an element here if the base 2 representation of that element is longer than the base 3 representation of that element. Well, note that the base 2 representation of the number 2 requires 2 digits, whereas the base 3 representation of the number 2 only requires 1 digit, and 2 digits is more than 1 digit, so I'm going to draw an arrow from 2 to 2. I'm not going to draw an arrow from 2 anywhere else because the base 2 representation of 2 required 2 digits, and there are no other numbers in our set whose base 3 representation requires less than 2 digits. These all require exactly 2, this requires 3. So the only arrow leaving 2 goes to 2. What about 3? Well, really, for 3, it's going to be the exact same. I'm going to draw an arrow from 3 to 2, and that's because the base 2 representation of 3 requires 2 digits, but the base 3 representation of 2 only requires 1 digit. And much like I did with 2, I'm not going to draw any more arrows from 3 because there are no other elements in my set whose base 3 representation uses less than 2 digits. What about 5? Well, my base 2 representation of 5 requires 3 digits, so I'm going to draw an arrow from 5 to any elements over here whose base 3 representation requires less than 3 digits. Well, let's see, it looks like that's everything except for 9, right? All of these require less than 3 digits. So from 5, I'm going to draw an arrow to 2, 3, 5, and 8. What about 8? Well, 8 and 9 actually, both their base 2 representation, they each require 4 digits. And every single base 3 representation that I have requires less than 4 digits. So I'm going to draw arrows from both 8 and 9 to every other element. I'm going to draw an arrow from 8 up to 2, from 8 to 3, from 8 to 5, from 8 to 8, and from 8 to 9. And then I'm going to draw an arrow from 9 to 2, from 9 to 3, from 9 to 5, 9 to 8, and 9 to 9. Probably could have color coded that to make that a whole lot neater and easier to see. Sorry about that. Maybe you will do that. Maybe you won't. Who knows? Okay, so I guess this is my arrow diagram, and I'm going to call that good. Had you made yours a little bit neater, it might have been easier to answer these questions. For me, it might be a pain because this is so messy, but I will try my best. Reflexive. In order for a relationship to be reflexive, there must be an arrow from every single element to itself. So there's an element from 2 to 2, that's a good sign. However, there is not an element from 3 to 3. Reflexive sure is not. Maybe I don't need the exclamation point. No, because the element 3, 3 is not in our relation, is not in R. I don't know if I call my relation R. No, whatever. It's not in the relation. So that makes it not reflexive. And you're like, but there's an arrow from 2 to 2. There's an arrow from 5 to 5, from 8 to 8, from 9 to 9. Yeah, that's all great. But to be reflexive, there has to be an arrow from every single element to itself. So just one case of a missing arrow is enough to make it not reflexive. So this thing's not reflexive. What about symmetric? In order to be symmetric, anytime I have an arrow from one element to another, I must have another arrow from that second element back to the first. So what I'm saying is there's an arrow from 5 to 8 right here. There's an arrow from 5 to 8. So there better be an arrow from 8 to 5. Oh, there is. Okay, good. So it's symmetric? Not necessarily. That has to be true for every single arrow. So, for example, there's an arrow from 3 to 2, but there is not an arrow from 2 to 3. So this thing is not symmetric either. So I could write 3, 2 is in R, but 2, 3 is not. There's an arrow from 3 to 2, but there's not an arrow from 2 to 3. In order to be symmetric, anytime I have an arrow of this type, I have to have the corresponding arrow of this type. I don't, it's not symmetric. What about transitive? It's the one everyone loves. And by loves, I mean hates. Okay, in order to be transitive, if I have an arrow from, I don't know, 5 to 3, for example, and then another arrow from 3 to 2, there must be an arrow straight from 5 to 2. It's kind of the shortcut rule. If I go from 5 to 3 and then 3 to 2, there must be an arrow from 5 to 2. So in this case, there's an arrow from 5 to 3, and there's an arrow from 3 to 2, and yeah, there's an arrow from 5 to 2. That's fantastic. But that does not make it transitive. In order to be transitive, that property that I just described has to always hold. So the question becomes, can I find a case where I have an arrow, say, from 5 to 8, and another arrow from 8 to 9, so that there is not an arrow from 5 to 9? I think I just described the case. Transitive? Sure is not. Why not? 5, 8 and 8, 9 are in R. But the shortcut from this 5 all the way to this 9 is not. If I find one case where it's not transitive, the entire thing is not transitive. So even though there's a lot of cases where it appears to be transitive, it has to always be transitive in order for me to call it transitive. It's not. The answer to that question is no as well. Is it an equivalence relationship? Hell no. Can't spell. Equiv. I won't try to spell. I guess I kind of do. Equivalence relation, question mark. No. In order to be an equivalence relation, my answer to all three of these questions must have been yes. They're not. In fact, they're all no, but I don't even need them to all be no. I just need one of them to be no. No. It's not symmetric, transitive, and reflexive. It's not all of those things. I didn't answer yes to all of the above. Maybe that's more clear. No, I did not answer yes to all of the previous questions. Again, to be an equivalence relation, it must be reflexive, symmetric, and transitive. It is certainly not all of those things. So it's not an equivalence relationship. Finally, a function. It's not that either. It's not a function. Why is it not a function? In order to be a function, there must be at most one arrow leaving any element. So pick on 5, for example. From 5, I got arrows all over the place. So I map 5 to 2. I map 5 to 3. That's enough to say it's not a function. Is it a function? No. There is more than one arrow leaving an element. Five, 2, and 5. That's not a 5. 5, 5 are in our comma, for example. So there you go. It is not reflexive, it is not symmetric, it is not transitive, it is not an equivalence relation, and it is not a function. I think I've answered all these questions. I drew my arrow diagram, so I'll stop this video right here.